The focus of the videos so far has primarily been discrete probabilities. Recall that in a discrete probability setting, a discrete probability function tells the probabilities at specific values. A discrete random variable takes inputs in your sample space and outputs a real number. Finally, the PDF tells the probabilities of specific outputs. To give an example, imagine that you roll 2 dice. To keep things easy, I'm going to imagine that one of them is white and one of them is red. The sample space are the pairs of dot patterns on the 2 dice. If I roll 3-dot pattern, typically called a 3, on the first die, that would be 3 dots. If I roll 4 dots on the second die, that's the 4-dot pattern. This can be mapped into the real numbers by adding up the number of dots. Typically, if people rolled the dice as I described, they would say that they had rolled a 7. That's the discrete random variable. It took the sample space of dice rolls, it output something. The PDF will tell the probability of that output. In this case, what is the probability that if you roll 2 dice, they add up to 7? A bit of computation shows you that will be a 6th. Now, however, we're going to turn to the continuous setting. You've seen before what a continuous probability function is. We also can talk about continuous random variables. A continuous random variable, again, takes values in a sample space and maps them to the real numbers. It has a corresponding probability density function, typically called PDF, but rather than defining the PDF as being the probability of a specific output, we're going to have to define it in terms of intervals. The reason for this was discussed previously, and it is that because you have infinitely many outputs, and typically there's sort of similar likelihood, the probability of specific points is 0. Instead, we look at a different property of PDFs, which is that if you want the probability of your answer being in a certain range, you add up the probabilities at the points in that range. In the continuous setting, adding up probabilities becomes integrating. So the PDF is a function that when you integrate it, you get the probability of being in an interval. Consider the following example. You have a random variable y. Its PDF is given, as you see here, in 2 different parts. I don't need to know the sample space. I don't need to know how it was mapped into the real numbers. All I need to know is the probabilities that the answers had certain values. Now, I look at the probability of an interval. In the continuous setting, we do not add, we integrate. So since I want to know probability from 0 to a half, I integrate from 0 to a half. Looking at the PDF, 0 to a half lies entirely within that region 0 to 1. So I can replace fy with y. Then it's a straightforward integration. Y squared over 2, you have your upper and lower limit, you substitute them in, and the probability is 1/8. Now turn to a more complex example, which on the surface is not really any different. The probability that you pick a value between -1/2 and 1/2. I've chosen to write it in the same notation that was given at the top, with a less than or equal to y less than or equal to b, but it could also have been written in that closed interval notation. So I'm integrating from -1/2 to 1/2 of the PDF. However, the setting is a bit trickier now, because this interval from -1/2 to 1/2 includes multiple components of that PDF. Consider the color-coded diagram here. Up until -2, the PDF was 0. From negative 2 to negative 1, it was a half. Then it was 0 for a while. Then it was y. Then it was 0. The region of interest here from negative a half to a half is indicated by this yellow region. Notice that part of it is in that red 0 region. Part of it is in that blue y region. None of it is in that blue 1/2 region. So the integral only considers that truncated centerpiece. From negative a half to 0, I'm integrating 0. From 0 to a half, I'm integrating the other part, y. The first integral is a 0. The second integral is a standard polynomial, y squared over 2 with your upper and lower limits. Put in those limits, and the answer is 1/8.